Hi, I'm Rakshith from Max Planck Institute of Informatics in Germany. I'll talk to you about a new way to test computer vision models through semantic adversarial data generation. Evaluation in computer vision is often done with fixed test sets drawn from IID distribution to training data. Yet recent works have shown that models which perform well on IID data break down under distribution shifts. This includes presence of noise or changes in context. This implies that IID testing alone is not a sufficient criteria of model's performance. In our work, we propose an adaptive testing approach. We develop a system to generate hard test samples targeted to a specific model through semantic adversarial attacks. Unlike a standard LP-norm attack which makes small imperceptible changes to an image, our semantic adversary makes large visible changes to an object's appearance to fool the target detector, while still looking plausible to a human eye. An example of this is shown here with the cow's appearance being edited by our system to fool the detector to see a horse. We achieve this through constrained adversarial optimization of the target object's appearance through a generative model. This process allows our system to efficiently explore the data manifold and find the failure modes of the model being tested. Our system consists of three main components. First is an object synthesizer with disentangled representation of object's pose and appearance. It enables editing an object's appearance without affecting its pose. Second component is the adversarial optimization of an object's appearance to fool the detector using the synthesizer network. Finally, we impose constraints on the appearance optimization to keep the synthesized object realistic and within the class manifold. Let's take a deeper look into the synthesizer network's design. Our synthesizer is a generative model which takes two objects as input. First provides a target shape and second provides a target appearance. The synthesizer combines these two to generate a composite object with the right pose and appearance. Internally, the synthesizer has an encoder-decoder structure. It employs two independent encoders, one for representing shape and the second for representing appearance. The shape encoder is a convolutional network with unit structure. It outputs a binary part segmentation spatial map indicating which of the k parts is active at any given location. Note that here the parts do not necessarily have a semantic meaning. Instead, they are the decompositions of the object which are most beneficial in synthesis. Since the output part maps are one-hot vectors at each location, they act as information bottlenecks which only allow spatial information to pass through this path. Many prior works utilize Gaussian keypoint bottlenecks. However, in our experiments we found that our part segmentation bottleneck scales better for diverse object classes. The appearance encoder is also a CNN with unit structure. It produces one vector summarizing the appearance information for each location. This is combined with the previously obtained part map to get just one appearance vector for each part. Since the appearance codes do not have spatial dimensions, the amount of shape information in this path is limited. This allows our network to successfully disentangle the shape and appearance representations. Finally, the decoder network combines the pose and appearance codes produced by these two encoders to generate the final object. A challenge in training the synthesizer network is the lack of paired training data of same object instance with different appearances. We overcome this by applying autoencoding and GAN-based training signals. The reconstruction laws can be applied for the autoencoding paths or the cyclic autoencoding paths where final target shape and appearance come from the same object instance. The GAN laws, on the other hand, can be applied when appearance and shape targets come from two different instances by training the synthesizer network to generate an object which is realistic as per a discriminator. Next, let us see how we can use the synthesizer network to generate hard test cases. As discussed before, our synthesizer network allows us to edit appearance of an object without affecting its pose. This is illustrated here where the appearance of the bus is slowly interpolated from left to right while keeping its pose fixed. The interpolation produced by our model is smooth and works better than using Gaussian keypoints, which is commonly applied in prior works. Now one could simply adversarially optimize the appearance code of an object to fool the detector. However, this often leads to degenerate solutions since the adversary generates objects with completely unrealistic appearances. Hence, we propose a simple but effective mechanism to constrain the appearance code during the adversarial optimization. Given a target instance, we first select a few examples of the same class from the training set to guide the optimization. Next, we constrain the optimized appearance vector to remain within the convex hull spanned by the appearance of these guiding instances. This is done by optimizing the interpolation coefficients A instead of the appearance codes V as shown in these equations. While this constraint is not foolproof, we found that it works well in practice. Here's an example of the optimization. We start from a reconstruction of the bird at iteration 0 and edit its appearance to drop the detector's confidence. By step 6, the detector mistakes the bird for a dog, and by the 10th step, the detector confidently sees a dog with a frisbee, fooled by the yellow disc-shaped feather in the new appearance. Next, we evaluate our semantic adversarial data in terms of effectiveness, realism, and usefulness for training. To measure effectiveness, we attack the YOLO v3 detector on the COCO dataset. The performance of the detector drops by almost 20 MAP when the appearance of a single object is edited by our semantic adversary. Additionally, optimizing the position of the object drops performance by further 3 MAP. This is roughly equivalent in strength to standard L infinity norm attack on a single object with epsilon equal to 8 by 1255. If we edit 2 objects per image, the performance drops further to 46.5 MAP, making it a total drop of 57%. We conduct human study to verify if our generated data is realistic and interesting. First, we ask human judges if the generated object still belongs to the original class. In 93% of cases, the participants agreed that this is true and the class label is preserved. We also asked humans to rate the typicality of the appearance of the object on a scale of 1 to 5, with 1 being very rare and 5 being very typical. Human judges found that our semantic adversarial data has more unusual appearance compared to the original test data as seen in this graph. This evaluation verifies that our system generates hard examples with atypical appearance while still looking plausible to human eye. Our semantic adversarial data can also be leveraged to improve robustness of detectors by using it to augment training data. Our experiments show that it gives a small but consistent boost to detector performance on 3 tested datasets. However, a larger benefit is seen on generalization to out-of-distribution data where the detectors are tested on images from a different but related dataset. For example, on the COCO dataset, adding our semantic adversarial data to the model training improves the performance on the IID testset by 1.1% relatively. However, the same model shows a 4.9% improvement when tested on the Unreal dataset, which contains objects in unusual context. Additionally, our experiments find that our semantic adversarial data is complementary to latest data augmentation techniques like auto-augment, showing a small added benefit. Find more results and ablations in the paper. Qualitatively, our novel testing strategy finds various failure modes of the detector. We show examples from 4 categories next. First is an example of camouflaging. The adversary edits the appearance of the stop sign to blend with the background, causing a misdetection. Other failure modes include misclassification caused by an unusual appearance, as seen here with the motorcycle being misclassified for a backpack. The adversary also exploits a combination of context and appearance to cause misclassification, as in the case of this person mistaken for an airplane after editing. Finally, when optimizing position, the adversary causes mistakes by creating occlusions. The lady here is moved in front of the dog to cause a misdetection. To summarize, we present a new way to test computer vision models by generating tailored hard examples through semantic adversarial attacks. This is achieved through a combination of disentangled synthesizer design and constrained adversarial optimization to generate hard examples with unusual but plausible appearances. Our system finds novel failure cases in the detector while also being useful in training to improve the model robustness. Thank you for listening. Please come talk to us in the live session for further discussion.